to talk a little about a side project we had with NASA, GIS, and Columbia University on the implications of biomass burning, dust, and industrialization or anthropogenic air pollution, their health impacts in Africa. That study was led by Susanna Barr from NASA GIS and her PhD and postdocs from Columbia and myself for the health impact assessment. And you can see here in this plot that we geographically we have differences in PM2, PM2.5 or PM5 pollution. Globally, you may have natural sources, anthropogenic sources, or biomass burning sources, and they vary in time and space. And one thing that we really consider is this biomass burning impact over Africa or the Amazons, and how much they contribute to premature mortality. And you can also see in the right panel that during the biomass burning season, which is mainly anthropogenic in Africa, below the sub-Saharan region, you get very high levels of PM pollution, and it's also transported long distance. So based on that, we know that the sub-Saharan Africa produces about a third of the whole Earth's biomass burning aerosol particles. So we think that there should be an important impact on this on human health. And we also know that majority of these emissions, biomass burning emissions, are linked to agricultural practices actually. So they are anthropogenic, not natural. In addition, Central Africa, it also experiences the largest lightning flash rates globally. So this is contributing to the natural part of the biomass burning emissions. So Africa in general has a combination of anthropogenic dust, or we can say natural, and biomass burning emissions, and they also interact. For example, anthropogenic fires or biomass burnings can change the dust storm frequency and through climate feedbacks and their locations, so that they might have different implications on transport. So this is very complex atmospheric composition and sources in Africa, and this is further complicated by a fast-growing society, which was already mentioned in the previous talks. And Africa is currently the fastest-growing population in the world. So based on this background, the main motivation was that the African countries such as Nigeria and Egypt are globally within the leading countries of air pollution mortality. Studying mortality or health impacts in Africa is quite few. They are severely understudied because of the obstacles in the political and societal ways. There's a real lack of epidemiological studies, and there are also a lack of observational data sets of pollution. And when we look at the literature about the health impacts of air pollution in Africa, which are quite few, most of them are from global studies, but there are also some locals. But we see very large variations in the numbers of calculated premature death. You can see they vary about from 170 to 80,000 million, and they can go up to over 1 million or 2 million, depending on which sources you get. So there's a large variability in the literature. So we decided to contribute into this large variability, and we used the GIS model, the Earth System model developed by NASA GIS, which is a rather coarse resolution, together with the microphysical model and the interactive fire model. So we can actually distinguish if the fires are anthropogenic or natural. And this is important because we are not only making one base simulation where we include everything, we also have 3 other simulations where we simulate only the natural aerosols or natural sources, biomass burning sources, and anthropogenic sources. So in that respect, distinguishing the biomass burning between anthropogenic and natural plays a different role. We actually did run the model for a very long period from I think 1750s until 2100, but that was for another purpose. Studying the biomass burning, we for now only looking at 2016, but we are planning to increase this number of years to get also a time series. And this part is the air quality, so to speak, modeling part. And then for the health impact assessment, we use the EVA model developed at Aarhus University. It's a impact chain pathway model, and it uses concentrations and populations over the same grid, and it calculates different mortality and morbidity outcomes. We can distinguish between acute and chronic mortality. Although the title was health impacts, I will only focus on mortality in this talk. And we can calculate this health impacts based on ozone, CO, SO2, and PM2.5 currently, but we are also almost ready with implementing NO2 in the Nordic Welfare Project. And we also have an age distribution in the models, so we distribute the population to 5 different age classes representing babies, children or teenagers, adults, and then elderlies. And based on this population distribution and exposure response functions, we can calculate acute and chronic mortality. One important aspect that EVA model currently uses linear exposure response functions, which is quite reasonable for areas like Europe maybe, but areas where you have very large PM, either natural or anthropogenic like China or Africa, you might get actually quite overestimations using linear response functions. So this is something that we're aware of. And there will be some studies later this year that we will start implementing also nonlinear exposure response functions in EVA system, and then recalculate these results and see if the difference is high. And then some model evaluation here. You can see on the upper panel the aerosol optical thickness. As we said, there is not much data in Africa surface data in Africa to validate your models. Therefore, we use satellites in this case, and also the IRONET, which is a ground-based aerosol optical thickness. And on the upper panel, you can see the MODIS overlaid with the IRONET observations. And on the lower, we also add the GIS model. These panels are changing based on seasons. And overall, the model is doing a reasonable job in terms of seasonality. And so we are not very off from the PM values, but of course there are underestimations. And they definitely add uncertainty to the results. And some more model evaluation for different parts, but now on time series, and you can see that we generally calculate the general temporal variation. But we can also see that both models and satellites, they show biases if we compare to IRONET, and where they show biases depend on many factors. For instance, the MODIS data is biased high over the ocean due to the relatively high amount of clouds. The Calypso data, for instance, it's missing peaks, concentrations due to their sampling. And the GIS model, there's also a GIS 5 model that contributed to this work, but that's for the other part of the study, so I'm not mentioning a lot on that. But we can see that the GIS model is also getting the general at least geographical variation of the pollution and the levels. And then we use this population and then concentrations to calculate the total premature death. This is total everything, PM for chronic mortality, ozone and SO2 for acute mortality, and we sum everything here. And you can see we get a quite large number, 780,000 premature death for the year 2016 under these concentrations. And you can also see the spatial distribution. They are very, very much everywhere, but you can see very high spots below the Saharan desert and also on the western and eastern parts of Africa. And then when you go further south, the numbers get lower, but I'll come back to that. We also calculated the anthropogenic contribution to this 780,000 using the anthropogenic simulation, and we can see that the anthropogenic actually is quite low compared to the total number. It's 180,000 per year. However, the natural contribution, which is mainly PM2.5 in this case, coming from dust, it's quite large, 550,000, and it coincides very well with the total premature death, especially over the northern part of Africa, where we have large dust sources. And then you can see the biomass burning contribution. It's only 43,000 per year. It's quite low, given that Africa has the largest biomass, almost biomass burning source in the world, but the health part of this contribution is quite low. And when we break down into regions, we can see that the Sub-Sahara has the largest population density, but low PM2.5 levels. But because of the largest population density among the other three sub-regions, West, Central, and Southern Africa, it has the highest premature death numbers. And then we can also see that the West African part has the highest contribution of PM2.5 to mortality. Almost 74% of total mortality in the West African region was calculated to be PM2.5, and this is because the West African region has the highest PM2.5 levels. When we come to Central Africa, we see that the biomass burning has the largest impact. Almost a little bit more than half is coming from biomass burning. They also have the highest ozone levels, so together with biomass burning and ozone, they also have large numbers, but compared to Sub-Saharan or the West African domain, they have relatively low number. And then when we come further south to South Africa, we see the lowest mortality, because and the highest anthropogenic contribution of 77%, but the lowest mortality is because when you compare these four areas, they have the lowest PM2.5 and ozone. That's because it's a highly populated area, so the ozone levels tend to shrink, and the natural sources are much more limited, so the PM2.5 levels are quite low compared to, for instance, Sub-Sahara. And I also present a table on the right, the top leading causes of death in Africa 2005 per 100,000 people, and there you can see the lower respiratory disease and HIV has the highest share. And if you compare our numbers, 780,000, well, we are between the first and the second if we trust these numbers. But I think it clearly shows that air pollution has a very large impact over premature mortality in Africa. So coming to my conclusions, we said that it has the largest space-detectable aerosol plumes, especially biomass burning. This biomass burning is responsible for less premature deaths in Sub-Sahara than other anthropogenic regions. We calculated 43,000 premature deaths. We also found 180,000 premature deaths caused by anthropogenic sources in Africa. However, the natural contribution, especially by dust, is 550,000 by PM2.5. And with these numbers, we are definitely in the top part of the causes of death in Africa. But we also have some discussion about these numbers. We are aware that these rates we calculate, they represent a kind of probably upper bound due to the linear exposure response functions, because that's why we are trying to implement a nonlinear exposure response function in order to test these results, because in the nonlinear functions you might get lower responses when you get higher PM2.5 concentrations. So you get more steep curves in the lower concentrations and less in the high. And since Africa is in the high end, these results might be overestimated. And another downside is that we need more epidemiological studies, since EVA model currently uses exposure response functions coming from Europe or North America, which is not, of course, representative of the African conditions. So we are also have large uncertainties in terms of that. But overall, we don't think that the number is highly off. Maybe we will get a reduction if we introduce more proper response functions and nonlinear, especially, but the numbers will still be high, we believe. And we are going to test it in the next phase. So thank you very much.
Thank you, Ulas.
Thank you.
Any short question or comment? Ulas?
Thank you very much for coming here and talk today. Very interesting. We've been discussing this with the mortality and air pollution in Africa during our Tuesdays here at Pufendorf Institute, and we've been thinking about both that Africa in general, I mean it's a big continent, it's a lot of countries, but in general has quite a young population. Yeah. So when you calculate the mortality, maybe we in a way also underestimates the health effects, which is only calculated in you have to be above 30 to have a mortality effect.
You can see in this table that the young population is more or less half. Below 15 is 43%. This month's number is much lower in Europe and North America, for instance. So you're right. A very young population.
Yeah, and when we've also been discussing this with mortality exposure response function. About using this Pope et al., which is comparing different cities. And we used it in a local study. We used response function that took account into the local variation. And for example, when you, Michael Jarrett here, we did this American, and we saw almost a double mortality impact using more recent studies. But it's a very interesting study, and we're happy to follow your work.
Thank you.
Just, I guess one of the concerns I have with this kind of work, which I think is very interesting and highly needed, but you know, when you look at the crustal material and the dust, very, very few primary studies show there's any effect. The biggest study that was ever undertaken, we did it in the U.S. with 450,000 people, absolutely no effects. So. It, for me, raises an issue. Like, I think, it's one thing to extend PM2.5 estimates from Europe to Africa, reasonable to maybe say we have so much evidence that they cause effects. Yeah. When you start taking a function and you say this dust is the same as burning fossil fuels or biomass, that raises questions for me about whether, we really need more primary studies before you can make that leap, I think.
I agree. I mean, we basically assume that PM2.5, the chemical composition in PM2.5 is homogeneous, so everything is as toxic. So yeah, that's a big assumption. I know.
Okay, thank you so much.
Thank you.